1958. A suburban kitchen in Levittown, New York. A hand grips the top edge of a bag of Lay's potato chips. With a decisive tear of the waxed paper, there is a sharp hiss, the sound of an inert atmosphere, a carefully engineered environment of pure nitrogen escaping into the room. Inside, a cascade of impossibly uniform golden-yellow discs of potato, each one a near-perfect circle, glistening with a precisely metered film of salt and oil. The first chip is selected, it is placed on the tongue, and with a slight pressure it breaks. The sound is not a simple crack or a crumble, but a complex crystalline fracture that registers as the definitive, satisfying crunch. This moment of mundane perfection, repeated in millions of homes across America, was no accident. It was the end result of a victory in a quiet but continuous industrial war. The story of this flawless consumer experience begins not in the kitchen pantry, but in a conflict waged across laboratories, processing plants, and packaging lines. It was a war fought not against a military opponent, but against the fundamental forces of chemistry, physics, and time itself. The enemies were oxidation, microbial growth, moisture, and the inherent fragility of the product. The outcome of this struggle would prove that a simple snack could represent a triumph of process control, logistical engineering, and a new doctrine of mass-produced consistency. In the early decades of the 20th century, the potato chip was a purely local delicacy, a product not of centralized factories, but of individual delicatessens and small storefront confectionaries. The process was one of craft, not industry. Potatoes were fed one by one into manually operated slicers, producing wafers of wildly inconsistent thickness, some varying by whole millimeters within a single batch. These were fried in open kettles of animal fat, typically beef tallow or pork lard, where temperature control was a matter of intuition, not instrumentation. The result was a product defined by its randomness. Some chips emerged pale and overly greasy, their starches barely gelatinized. Others were cooked to a dark, bitter brown. Salt was applied by a handshaker, a method guaranteeing a distribution that ranged from bland to overwhelmingly saline. The most critical failure, however, was a matter of fundamental chemistry. Once cooked and cooled, the chips were scooped into simple paper bags, or for a premium waxed glassine envelopes, often stapled shut at the top. This packaging offered no meaningful barrier against the atmosphere. Oxygen immediately began its assault on the lipids of the cooking fat, a process of oxidation that produced noticeable rancidity in as little as 12 to 18 hours. Simultaneously, the dehydrated potato starch acted as a powerful desiccant, aggressively absorbing ambient water vapor. This moisture ingress systematically destroyed the brittle, glassy structure achieved in frying, turning the signature crunch into a soft, leathery chew. The arithmetic of this decay was unforgiving. A product with a viable shelf life measured in hours, not weeks, could never be more than a hyperlocal novelty. Compounding this chemical instability was an equally devastating structural problem. The very nature of batch kettle frying created a delicate, non-uniform product, riddled with internal stresses and microfractures. Placed in a thin paper bag, the chips possessed zero protection from mechanical shock. The routine jostling of a delivery cart or the simple pressure of stacking bags on a shelf was enough to reduce a significant portion of the contents to a worthless collection of broken shards and greasy dust. A product that could not survive transport beyond a few city blocks was an industrial impossibility. The central dilemma was therefore established, not as a challenge of production volume, but as one of fundamental physics and material science. The pre-industrial chip was a logistical dead end. The solution to the logistical dead end arrived not from a chemist or a food scientist, but from a command-level perspective. In 1932, in Nashville, Tennessee, a 23-year-old entrepreneur named Herman Worden Lay purchased the manufacturing assets of the Barrett Food Products Company for $100, money he had to borrow. Lay was not a cook, he was a salesman. His initial work involved selling potato chips from the trunk of his Ford Model A, personally making deliveries to groceries, gas stations, and military bases. This direct ground-level experience with the product's failures, with crushed bags, rancid product, and wildly inconsistent quality, provided him with a terrible clarity. He recognized that the fundamental business was not about making potato chips, it was about delivering them. Where others saw a simple snack, Lay saw a complex logistical puzzle. His vision was therefore not one of mere culinary improvement, but of systematic conquest. He envisioned a single, branded, uniform product available on a shelf in every town, a goal that was completely at odds with the physical and chemical realities of the product as it existed. A chip with a shelf life of 18 hours could not cross a county line, let alone a state line. A product that turned to dust in a paper bag could not survive a regional distribution network. Lay's ambition required a complete rethinking of the dominant production doctrine. To achieve national scale, he understood he would need to solve the three core failures identified by the physics of the problem. First, the randomness of craft production had to be replaced with the disciplined consistency of mechanized, instrument-controlled manufacturing. Second, the chemical and structural decay native to the product required a new science of packaging, an engineered container that could serve as a stable, inert environment. Third, and most critically, the hyperlocal delivery model had to be supplanted by a purpose-built logistical network, a private army of salesmen and delivery trucks managed with military precision. This was not a plan to sell a better snack. It was an industrial blueprint for achieving shelf-stable mass-market ubiquity, a challenge that was, at its core, an engineering problem of unprecedented scale. The first front in this war for consistency was not waged with stainless steel machinery, but in the laboratory. Even as early mechanization began to standardize slice thickness and frying times, a stubborn randomness persisted in the final product. Batches of chips fried under identical conditions, the same oil temperature, the same duration, the same salt application, would emerge from the fryer with inexplicable variations in color. Some were the desired pale gold, while others were a dark mottled brown, carrying a distinct and commercially fatal bitterness. The problem appeared to be a form of industrial chaos, an unsolvable variable that threatened the entire enterprise of mass production. The search for the source of this inconsistency led food scientists of the era to a fundamental re-examination of their primary raw material. The investigation revealed a critical truth. The enemy was not a flaw in the process, but a hidden characteristic of the potato itself. This aha moment came with the identification of a simple but powerful chemical agent, sugar. Specifically, the variable levels of reducing sugars, primarily glucose and fructose, within the potato. The browning and flavor development during frying was governed by the Maillard reaction, a complex cascade of chemical changes that occurs between amino acids and these reducing sugars at high temperatures. It was the same reaction that gives a pan-seared steak its crust or a loaf of bread its golden brown color. The implications for the potato chip industry were staggering. Potatoes harvested in the early fall, like the Kennebec or Katahdin varieties favored by the industry, might have a reducing sugar content of less than 0.5% by weight. When fried, they produced the perfect light golden chip. However, potatoes are living organisms. To protect themselves from freezing, tubers stored at low temperatures, typically below 45 degrees Fahrenheit or 7 degrees Celsius, begin a process called cold-induced sweetening. Starches within the potato cells are enzymatically converted into reducing sugars. The longer the storage period, the higher the sugar concentration. A potato stored for several months over the winter could see its reducing sugar content climb to 2 or even 3%. The arithmetic of the Maillard reaction was unforgiving. Fed into a fryer, these high-sugar potatoes browned aggressively and unpredictably, the accelerated reaction producing bitter-tasting compounds long before the chip was properly dehydrated. The result was a product that was simultaneously burnt and soggy. This discovery provided a terrible clarity. The quality of the final chip was being dictated not by the factory, but by the calendar. To achieve year-round consistency, the producer had to declare war on the potato's own seasonal biology. The battle for the perfect chip had to be won not at the fryer, but in the storage silo. The discovery of cold-induced sweetening represented a paradigm shift. The battle for consistency could no longer be fought exclusively on the factory floor. The front line had moved to the farm field and the storage silo. If the raw material itself was an unpredictable variable, no amount of process control could guarantee a uniform output. The solution, therefore, could not be found in better thermometers or more sophisticated fryers. It would have to be found in agricultural science. What the burgeoning industry needed was not a better process, but a fundamentally better potato. This realization triggered a systematic search for the ideal industrial tuber, a potato designed not for the dinner plate, but for the automated production line. The technical specifications were exacting. First, it required exceptionally low levels of reducing sugars and, crucially, a genetic resistance to the sweetening process during cold storage. Second, it needed a high solids content, or a high specific gravity. While a common baking potato might have a solids content of 18%, the target for a chipping potato was over 20%. This higher starch concentration meant less water to be cooked away, resulting in a faster frying time, a crispier final texture, and, most importantly, significantly less oil absorption. This single characteristic translated into massive cost savings when scaled to industrial volumes. Finally, the potato had to possess a uniform, round shape with shallow eyes, a geometry that maximized yield by minimizing waste during mechanized peeling and slicing. The breakthrough arrived in 1948. It was not a new piece of machinery or a chemical additive, but a seed. Developed by the United States Department of Agriculture's National Potato Breeding Program, at their station in Presque Isle, Maine, it was a cultivar initially designated B75. Released to the public, it was given a name that would become synonymous with the industry, the Kennebec. The Kennebec potato was a triumph of agricultural engineering, a weapon built to defeat biological randomness. The Kennebec met every requirement. It exhibited consistently low sugar levels, a high specific gravity, and most critically, an unprecedented resistance to accumulating sugars even when stored for long periods at a commercially necessary 45 degrees Fahrenheit. Furthermore, it was resistant to late blight, the very disease that had caused the Irish potato famine a century earlier, ensuring a more stable and predictable supply chain. The adoption of the Kennebec by large-scale producers was not merely an upgrade, it was a fundamental shift in operational capability. For the first time, a manufacturer could purchase a massive harvest of potatoes in the fall, hold them in storage through the winter, and produce a perfect golden yellow chip in March that was chemically and physically indistinguishable from one made in October. The problem of the calendar had been solved. The war against the potato's own chemistry had, in effect, been won, not by fighting it, but by breeding it out of existence. But the development of the Kennebec potato, a decisive weapon in the war against chemical variability, represented only half the solution. A uniform raw material was useless without a uniform supply, and the arithmetic of national-scale production revealed a staggering logistical deficit. A factory designed for continuous 24-hour operation required a constant inflow of potatoes 365 days a year. The autumn harvest, even of a superior cultivar like the Kennebec, provided a massive glut of product for 3 months, followed by 9 months of scarcity. The victory in the laboratory and the breeding field had opened a new, more complex front in the war for consistency, the battle against geography and the calendar. The problem was no longer one of quality, but of overwhelming quantity and year-round availability. The solution was a campaign of unprecedented logistical and agricultural scope. The industry began to operate not on a single harvest cycle, but on a near-continuous one, turning the entire North American continent into a single coordinated farm. A system of contract farming was established across multiple distinct climate zones. The operational campaign began in the early spring, with the first harvest of Kennebecs from the winter fields of Florida. As the season progressed, the harvest line would move north, following the advance of warmer weather, through North Carolina in late spring, then to Missouri and the mid-Atlantic states in early summer. The main, massive harvest would still come from the traditional northern growing regions like Michigan, Wisconsin, Maine, and the Red River Valley of North Dakota in the fall. The effect of this geographic strategy was to create a rolling, year-round supply chain that fed the processing plants from April through October. But this still left the critical winter gap, from November to March, when no fields were producing. Even the resilient Kennebec could not be stored indefinitely without consequence. This final logistical challenge was met not in the field, but through an enormous investment in industrial infrastructure, the climate-controlled potato storage facility. These were not mere warehouses, they were massive, purpose-built life support systems designed to hold the potato in a state of suspended animation. Within these structures, some holding more than 60,000 metric tons of potatoes, the environment was managed with military precision. The temperature was held in a narrow band between 45 and 50 degrees Fahrenheit, approximately 7 to 10 degrees Celsius, a critical range that was cool enough to enforce dormancy and prevent sprouting, but warm enough to prevent the onset of cold-induced sweetening. Humidity was maintained at 95% to prevent moisture loss and shrinkage, which could cost millions of dollars in lost tonnage. Computer-controlled ventilation systems managed the atmosphere, purging the carbon dioxide that built up from the respiration of millions of living tubers. This system was the final piece of the logistical puzzle. A potato harvested in North Dakota in October could now be held in this technologically imposed stasis until the following March, emerging from storage with a chemical profile, a reducing sugar content below 0.25%, that was nearly identical to the day it was harvested. The factory gates could now be supplied, without interruption, forever. The seasonal nature of agriculture had been defeated by an engineering and logistical doctrine of overwhelming force. With the logistical campaigns won, the battle for consistency now shifted from the continental supply chain to the factory floor. Here, a steady, unbroken river of Kennebec potatoes, uniform in chemistry, size, and specific gravity, arrived at the first instrument of their mechanical transformation. Having defeated the randomness of biology and the tyranny of the calendar, the raw material now faced an enemy of a different order. The inherent variability of its own physical form. The fight for the perfect chip was about to enter the domain of pure physics, where victory would be measured in thousandths of an inch. The central challenge was one of heat transfer. The frying process, the next critical stage, was not a gentle browning but a violent dehydration, designed to turn the potato's starchy interior into a brittle, glassy matrix in under 3 minutes. The success of this operation was governed by an unforgiving arithmetic. Heat penetration is a direct function of thickness. A slice that was even 5/1000ths of an inch too thick would emerge from the fryer with its core undercooked, a pocket of moisture that would condemn the final chip to a soggy, leathery texture. A slice that was too thin would burn, its sugars caramelizing into bitter compounds long before its thicker counterparts were cooked. The commercial requirement for a perfect uniform crunch was therefore translated into a brutal engineering specification. Every single slice had to be identical, a mathematically perfect disc with a thickness of 60,000ths of an inch, approximately 1.5 millimeters, with a tolerance so narrow as to be almost theoretical. This demand for absolute geometric uniformity at an industrial scale gave rise to a new class of precision machinery. The dominant weapon in this fight was the centrifugal slicer, epitomized by machines like the Urschel Model CC. Here, potatoes were fed into the center of a high-speed rotating impeller, a vanned disc spinning at several hundred RPM. Centrifugal force, the same principle that holds water in a spinning bucket, flung each potato outwards against the inner wall of a stationary slicing head. This head was not a single blade, but an assembly of 8 individual razor-sharp blades, each one micro-adjusted and locked into position. As the potato slid along the wall at high speed, it was planed by these blades in rapid succession, producing 8 perfect slices per revolution. The result was an industrial avalanche of uniformity. A single machine, operating continuously, could convert over 8,000 pounds of raw potatoes per hour into a torrent of perfectly replicated wafers, each one a 60,000ths of an inch thick clone of the one before it. This was not merely cutting, it was the imposition of an abstract geometric ideal onto an organic object, repeated millions of times per hour with relentless precision. The slicer was the first point on the line where the potato ceased to be a product of agriculture and was remade into a standardized industrial component. With its physical form now dictated by the unyielding logic of the machine, each wafer was ready for the next, most violent stage of its transformation, trial by fire. The stream of 60,000ths of an inch wafers exiting the slicer represented a triumph of mechanical precision, but this very act of creation introduced a new, immediate chemical threat. Each cut, precise as it was, acted as a microscopic rupture, shearing open the potato's cell walls and releasing a fine, sticky film of free starch granules across the surface of every single slice. This starchy residue, invisible to the naked eye, was a fatal contaminant, an enemy that threatened to sabotage the entire operation at the next, most critical stage. The physics of this problem were unforgiving. In the 350-degree Fahrenheit environment of the continuous fryer, these free surface starches would not cook into a crisp, glassy structure. Instead, they would gelatinize almost instantly, transforming into a sticky, water-absorbent glue. The effect on the production line was catastrophic. Individual slices, painstakingly engineered for uniformity, would weld themselves together into dense, inseparable clumps of wet potato paste. The fryer would become clogged with a single unusable mass, bringing the entire multi-ton-per-hour process to a grinding halt. Any starch that did not contribute to this clumping would wash off into the cooking oil, creating a suspended haze of particles that would rapidly scorch, polymerize, and degrade the fat. This would impart a bitter, burnt flavor to the entire batch and dramatically reduce the oil's operational lifespan. The cost of this degradation, scaled across millions of pounds of oil per year, represented an unacceptable economic vulnerability. The countermeasure was not one of delicate handling, but of overwhelming force, a high-volume water wash. This stage was framed not as simple cleaning but as a critical chemical engineering step. Immediately after exiting the slicer, the torrent of discs was deposited into a flume or onto a vibratory conveyor through which flowed a continuous cascade of temperature-controlled water. The volume and velocity of the water were precisely calculated to create enough turbulence to physically dislodge the clinging starch granules, washing them away into a separate reclamation system. The process served a dual purpose. It not only removed the problematic starches, but also leached out any final, residual surface sugars, providing a last line of defense against inconsistent browning. The slices emerged from this bath chemically sanitized, their surfaces scrubbed clean. But in solving the problem of surface starch, another had been created. Each slice, now pristine, was also saturated with a film of surface water. Introducing this water directly into the fryer would not produce a potato chip. It would produce a violent, explosive eruption of steam. A new enemy had been identified: moisture. Before the trial by fire could begin, a final rapid dehydration was required. The final enemy was moisture. Having been scrubbed of their surface starch, the 60,000ths of an inch wafers emerged from their water bath chemically pure but physically compromised, each one cloaked in a film of water that would cause a violent steam explosion in hot oil. The counterattack was not thermal, but mechanical. The stream of slices was fed onto a vibratory dewatering shaker, where a high-frequency oscillation physically shook the bulk of the water away, and then passed under a bank of high-velocity air knives, jets of room-temperature air moving at hundreds of feet per second, that sheared the last microscopic droplets from the surface. The process was a rapid, final preparation for the trial by fire. The slices, now surgically clean and physically dry, were fed directly into the mouth of the operation's heart, the continuous flow fryer. This machine represented the final abolition of the craft-based chaotic kettle method. Where the old system relied on a single operator judging doneness by sight, the continuous fryer was a monument to automated precision. A stainless steel trough, often more than 50 feet in length, held up to 1,200 gallons of cooking oil, typically a blend of corn and cottonseed oil, maintained not at a target temperature, but within a precise thermal window of 350 to 365 degrees Fahrenheit. This temperature was governed by a complex feedback loop of sensors and external heat exchangers, a system that had to instantly compensate for the constant thermal load of thousands of pounds of colder, 80% water content potato slices entering the system every hour. This was not cooking. It was a continuous industrial process operating under the unforgiving logic of thermodynamics. The chaotic randomness of the kettle was replaced by a precisely choreographed ballet. The slices were not simply dumped into the oil, but gently deposited onto a moving, Teflon-coated conveyor belt that submerged them. A second, parallel conveyor above them, a submerger belt, ensured no slice could float to the surface and undercook. Slowly, methodically, this conveyor system guided the river of thousands of individual discs through the searing oil. The speed of the belts was not arbitrary. It was the physical expression of a finely tuned chemical equation. Every single slice, regardless of its position in the flow, was engineered to have a residence time within the oil of exactly 2 minutes and 45 seconds. In those 165 seconds, a violent transformation occurred. The water inside the potato cells flashed into steam, its explosive expansion creating the delicate, porous structure of the final chip. As the moisture was driven out, oil was absorbed, and the Maillard reaction proceeded to its perfect light golden conclusion. The slices entered the fryer with a moisture content of over 80%. They exited with a moisture content of less than 2%. This was the engineered moment of creation, where the raw material was finally transformed into the finished product. The continuous fryer did not simply cook chips faster or in greater volume. It imposed an absolute mathematical uniformity on the process, guaranteeing that the billionth chip produced would be a perfect crystalline clone of the first. The continuous fryer, a monument to thermodynamic precision, had conquered the physics of dehydration. But in doing so, it opened a new front in the industrial war, the battle for the cooking medium itself. The 200 gallons of oil held within the fryer's 50-foot trough were not a simple ingredient. They were a complex chemical system, a massive operational expense, and a component as critical and temperamental as any piece of machinery. To deliver a consistent product, the oil itself had to survive a continuous three-front assault, from the thermal stress of constant high heat, the chemical attack of atmospheric oxygen, and the relentless physical contamination from the product passing through it. The very choice of oil represented a strategic decision. The animal fats of the pre-industrial era, the beef tallow and pork lard of the kettle fryer, were chemically unsuited for the demands of continuous national-scale production. Their high content of saturated fatty acids made them prone to rapid oxidative rancidity, producing off flavors that were entirely unacceptable for a product intended to have a shelf life measured in weeks. The industrial solution was the adoption of highly refined vegetable oils, primarily a specific blend of corn and cottonseed oil. These oils were chosen for their neutral flavor profile and, most critically, their superior chemical stability at high temperatures. They contained natural antioxidants and a fatty acid profile less susceptible to breakdown, allowing them to endure the 365-degree Fahrenheit environment for longer periods. This move from animal to vegetable fat was not a culinary choice, but a strategic necessity, a victory in chemistry that extended the operational life of the most expensive consumable in the entire factory. But even the most stable oil could not survive the physical contamination inherent to the process. As thousands of pounds of potato wafers passed through the fryer each hour, they shed microscopic particles, fragments of potato and gelatinized starch known in the industry as fines. These fines did not simply float harmlessly. In the high-heat environment, they were quickly scorched, carbonizing into tiny black specks. These charred particles were not just passive debris, they were active chemical catalysts. They accelerated the breakdown of the oil, promoting the formation of free fatty acids that imparted a sharp, bitter taste and dramatically lowered the oil's smoke point. This process of polymerization would thicken the oil, increasing its absorption into the chips and throwing the final product's texture and mouthfeel completely out of specification. The arithmetic of this degradation was unforgiving. An unchecked accumulation of fines could render a 200-gallon bath of oil commercially useless in a matter of hours, a catastrophic economic failure. The countermeasure was not to change the oil, but to subject it to a continuous, aggressive life support system. The fryer was integrated into a massive external filtration loop, a set of mechanical kidneys operating 24 hours a day. A constant stream of hot oil was pumped out of the main frying vessel and forced through a multi-stage filtration system. This system typically involved a primary screen to remove larger particles, followed by a pass through finely woven paper filters impregnated with diatomaceous earth, a porous microscopic fossil dust whose structure was ideal for trapping the smallest suspended fines. Cooled, scrubbed, and chemically rejuvenated, the oil was then pumped back into the fryer. This was not a batch process of cleaning, it was a dynamic steady-state equilibrium. The system was designed so that the rate of particulate removal perfectly matched the rate of particulate generation, holding the oil in a state of perpetual purity. This victory over contamination meant the difference between an operational lifespan measured in hours and one measured in days, turning an unpredictable chemical liability into a manageable industrial asset. The river of golden discs emerging from the fryer and its filtration system represented a product pushed to the very edge of mechanical and chemical perfection. Uniform in thickness, moisture content, and lipid profile, the chips were 99% of the way to their ideal state. But for an enterprise built on the promise of absolute uniformity, that final 1% represented a critical strategic failure. Despite the perfect potato, the precision slicing, and the thermodynamically controlled frying, a small, statistically predictable number of imperfections would always exist. A chip folded over on itself in the fryer, a stray chip that lingered too long near the heating element, a tiny speck of peel that had survived the abrasives. These were the final lingering ghosts of randomness. The traditional defense against these flaws was the human eye. Teams of inspectors perched alongside the conveyor belt were tasked with identifying and manually removing any chip that failed to meet the visual standard. But this practice represented the last bastion of pre-industrial fallibility in an otherwise ruthlessly optimized system. The human eye was a biological instrument, subject to fatigue, distraction, and subjective judgment. An inspector's standard for too dark could drift over the course of an 8-hour shift. The speed of the line, processing thousands of pounds per hour, meant that for every flawed chip an inspector caught, several others would inevitably slip past. In the arithmetic of mass production, this translated to millions of imperfect chips per year reaching the consumer, a direct contradiction of the core brand promise. Human quality control was no longer a solution. It was the final problem to be solved. The solution was not a better trained inspector, but the total abolition of human judgment from the process. This came in the form of the electronic color sorter. As the stream of chips cascaded off the main conveyor, they were funneled into a single accelerating layer that slid down a chute, forcing each individual chip to pass one by one through a zone of inspection. Here, they were illuminated by a constant standardized light source and scanned by a bank of photoelectric cells, electronic eyes that converted reflected light into a precise electrical voltage. A perfectly golden yellow chip would reflect a specific amount of light, generating a voltage within a narrow pre-approved range. A darker, scorched or blemished chip would reflect less light, causing a voltage drop. The result of this scan was fed into a simple but unforgiving comparator circuit. If the voltage for a given chip fell outside the engineered parameters for even a microsecond, the circuit triggered a solenoid, opening a high-pressure valve. A pinpoint jet of compressed air lasting only a few milliseconds would fire from a nozzle positioned just below the scanning zone, striking the single offending chip and knocking it out of the main product stream into a rejection bin. The good chips, untouched, continued their fall onto the next conveyor. Physics took over. The entire process, scan, analyze, reject, was completed in less time than it took a human inspector to even register a chip's existence. A single machine could do the work of a dozen inspectors with a level of speed and consistency that was a mathematical impossibility for a human being. It was an eye that never blinked, a hand that never missed, and a judgment that never varied. It was the imposition of industrial finality, ensuring that the only chips to survive the journey were the ones that met the unyielding specification of reproducible perfection. The torrent of flawless golden yellow discs cascading from the electronic sorter represented the culmination of a decade of industrial warfare. The enemies of biology, chemistry, and physics had been met and defeated on the factory floor. But this victory was dangerously incomplete. A chip, perfect at the moment of its creation, was a fragile and ephemeral thing. The story of its survival was a counterpart narrative, a parallel war fought not with slicers and fryers, but with polymers, seals, and atmospheric gases. The final critical battle was not for production, but for preservation. An intact, perfectly fried chip was strategically useless if it was stale or crushed by the time it reached the consumer. The initial attempts to solve this problem were born from the same technological era as the craft production they were meant to support. The stapled waxed paper bag, a slight improvement over the simple paper sack, offered a rudimentary barrier against the gross intrusion of ambient moisture. It could extend the product's viability from 18 hours to perhaps 48 or 72. But this was a tactical delay, not a strategic solution. The waxed paper was not a hermetic seal, it was merely a porous membrane. Its water vapor and oxygen transmission rates, while lower than plain paper, were still orders of magnitude too high to prevent the inevitable chemical assault. Oxygen molecules work their way through the paper's fibrous structure, oxidizing the lipids and producing the signature off-notes of rancidity. Water vapor did the same, systematically destroying the brittle, glassy structure of the chip. The arithmetic was still one of decay, simply on a slightly longer timeline. For a national distribution network requiring a shelf life of weeks, not days, it was a logistical dead end. The advent of cellophane in the 1930s appeared to be a breakthrough. Here was a material that seemed purpose-built for the modern era of mass-market goods. It was visually transparent, showcasing the golden uniformity of the product within, and it possessed barrier properties far superior to waxed paper. Heat-sealed cellophane bags represented a significant leap in capability, yet this too proved to be a flawed weapon. Early cellophane, derived from regenerated cellulose, was itself hygroscopic. It had a natural affinity for water. In humid environments, it could absorb moisture from the atmosphere, losing some of its structural integrity. In very dry environments, it could become brittle, prone to cracking and pinhole failures, especially along the folds and seals of the bag. The failure was fundamental. Both waxed paper and cellophane were conceived as simple containers, wrappers whose primary job was to hold a collection of objects together. They were not designed as stable, engineered micro-environments. They could not provide the two non-negotiable requirements for long-term preservation: a truly impervious barrier to oxygen and water vapor, and a durable structure capable of protecting a notoriously fragile product from the mechanical shocks of a national supply chain. The industry's ambition of shelf-stable, coast-to-coast ubiquity was being held hostage by inadequate material science. A new doctrine of packaging was required, one that treated the bag not as a container, but as an armored vessel. The failure of early materials like cellophane and waxed paper demonstrated a terrible clarity. The central challenge was not one of simple containment, but of waging a continuous multi-front war against the fundamental laws of chemistry. The architects of the modern snack industry realized that the enemy was not merely external contamination, but the very atmosphere itself. A potato chip emerging from the fryer with its carefully engineered 2% moisture and 20% oil content was a perfect fuel source for a devastating chemical reaction. The primary agent of this destruction was atmospheric oxygen, an invisible and relentless adversary representing 21% of the air in any warehouse, on any delivery truck, and on any grocery store shelf. The assault began at the molecular level, in a process known as autoxidation. It was a chain reaction of catastrophic efficiency. An oxygen molecule, often energized by an external catalyst, would attack the vulnerable double bonds in the unsaturated fatty acids of the cooking oil. This initial strike created a highly unstable molecule called a free radical, which would then viciously attack a neighboring fatty acid, propagating a cascading cycle of chemical ruin. The byproducts of this uncontrolled reaction were aldehydes and ketones, volatile compounds that registered to the human palate as the characteristic stale, soapy and paint-like off-flavors of rancidity. A perfect chip sealed in a merely adequate package was in effect a chemical time bomb, its countdown measured by the molecular ingress of oxygen. This chemical assault did not occur in isolation. It had a powerful accomplice: light. The energy from photons, particularly in the ultraviolet and blue portions of the visible spectrum, acted as a photosensitizer. This energy dramatically accelerated the rate of lipid oxidation, providing the activation energy needed to create the initial free radicals and quicken the entire destructive cycle. A bag of chips left on a sunny windowsill, or even under the constant hum of a supermarket's fluorescent lights, would go rancid at a rate several times faster than one kept in total darkness. The transparency of cellophane, once considered a marketing advantage, was now understood to be a catastrophic vulnerability. It was not a window for the consumer, it was an open invitation for the enemy's most powerful ally. The full scope of the problem was therefore established not as a single challenge, but as a set of non-negotiable engineering requirements for a new kind of defensive system. The ideal package had to engage and defeat two distinct enemies simultaneously. First, it had to win the chemical war by providing a near-perfect hermetic seal, a barrier with a transmission rate approaching zero for both oxygen and the water vapor that destroyed the chip's physical crunch. This barrier also had to be completely opaque, a shield to block the catalytic energy of light. Second, it had to win the physical war. It needed the structural integrity to withstand the crushing, puncturing, and abrasive forces of a national logistics network. The objective was no longer to create a bag. It was to invent a flexible, lightweight, and cost-effective composite material that could function as an armored, life-sustaining vessel. The search was on for an entirely new doctrine of preservation. The solution that finally broke the stalemate was not a singular miracle polymer, but a new doctrine of materials science, the composite laminate. Food engineers and polymer chemists realized that no single material could simultaneously provide the required structural integrity, printability, barrier properties, and sealability. The breakthrough was the understanding that these functions could be assigned to distinct layers, which were then laminated into a single, multifunctional film. This was not the creation of a bag, but the engineering of a flexible, lightweight armored wall. The technical teardown of this new weapon reveals a system of 3 layers, each with a specific combat role. The outermost layer, the public face of the product, was typically a film of biaxially oriented polypropylene, or BOP. The process of biaxial orientation stretched the polymer film in 2 directions, aligning its molecular chains to give it tremendous tensile strength and resistance to puncture and tearing. This layer was engineered to survive the physical brutality of the supply chain. It was also the print surface, reverse printed on its inner side so that the branding graphics were protected from scuffing, ensuring the product's visual integrity on the shelf. The heart of the system, and the decisive barrier against chemical and photonic attack, was the middle layer. This was typically a film of polyethylene terephthalate, PET, the same tough, clear polymer used for soda bottles. But onto this film, in a high vacuum chamber, a microscopically thin layer of pure aluminum, often less than 40 nanometers thick, was vapor deposited. The result was a metallized film that appeared as a brilliant silvered surface. This layer was the true hermetic seal. Its opacity was absolute, creating a complete shield against the catalytic energy of light and halting photooxidation entirely. More critically, it formed a near impenetrable barrier to gases. Where cellophane might have an oxygen transmission rate of 10 to 20 cubic centimeters per square meter, over a 24-hour period, the metallized laminate possessed a rate of less than 0.5. Its resistance to water vapor was similarly overwhelming. The enemies of rancidity and moisture had been locked out. The final, innermost layer was the food contact and sealant film, often made of cast polypropylene, CPP, or a polyethylene, PE, blend. This layer had 2 non-negotiable missions. First, it had to be chemically inert, incapable of interacting with or leaching into the high oil content chips. Second, it required a lower melting point than the outer structural layers. This allowed high-speed packaging machinery to apply heat and pressure to the bag's edges, melting only this inner layer to form a strong, permanent hermetic weld, a seal that locked the inert nitrogen atmosphere in and the destructive ambient atmosphere out. These 3 layers, the tough outer skin, the metallized barrier, and the inert sealant, were laminated together using specialized adhesives to form a single, unified sheet. This composite material was a triumph of systems engineering. It was a flexible fortress, a cost-effective material that provided a total defense against physical shock, light, oxygen, and moisture. The invention of this unassuming, crinkly bag represented the final, decisive victory in the war for preservation. It made a shelf life of not days, but 8 to 10 weeks, a logistical reality. The industrial ambition of coast-to-coast distribution was, at last, made possible. The composite laminate bag was a fortress, an armored wall against the external world, but a fortress is only as strong as its internal security. At the instant before sealing, the bag contained a captive enemy, a volume of ordinary atmospheric air. That air, composed of 21% oxygen, was more than sufficient to initiate the same catastrophic lipid oxidation the bag was designed to prevent. The arithmetic was inescapable. A hermetic seal around a pocket of reactive gas was not a solution. It was merely a smaller, more intimate battlefield. The war for preservation had to be won inside the package itself. The decisive countermeasure was a doctrine known as modified atmosphere packaging, executed in a swift final action, nitrogen flushing. On the vertical form-fill seal line, just milliseconds before the heated jaws of the sealer came together, a lance would descend into the open bag and inject a precise volume of pure food-grade nitrogen gas. The purpose was one of physical displacement. The jet of inert nitrogen drove out the lighter oxygen-rich ambient air, purging the internal atmosphere until the residual oxygen content fell from its atmospheric norm of 21% to a level below 1%. By replacing the highly reactive agent with a non-reactive one, the chemical chain reaction of autooxidation was starved of its fuel. The mechanism of decay itself had been disarmed. This final atmospheric intervention, however, achieved a second, equally critical strategic objective. The volume of injected nitrogen did not just create a neutral chemical environment, it positively pressurized the bag, transforming it from a simple container into a pneumatic cushion. This inflated pillow provided a buffer against the crushing and impact forces that had plagued the product since its pre-industrial origins. The delicate 60,000ths of an inch discs, which would otherwise shatter into dust under the simple weight of stacking or the vibration of transport, were now suspended and protected within their own pressurized vessel. This synthesis of material science and gas chemistry represented the final victory. It defeated the chemical enemy within and the physical enemy without, ensuring the chip that left the factory in a state of engineered perfection would arrive in the hands of the consumer weeks later and 1,000 miles away in precisely the same condition. With a product engineered to perfection and a vessel designed for its ultimate preservation, the industrial war entered its final campaign. The flawless protected chip was strategically complete, but for one final critical element, its flavor. The stream of hot, oil-coated discs emerging from the color sorter and moving toward the packaging line was pristine, uniform, and entirely bland. The challenge now was to apply a precise uniform coating of crystalline salt and flavor powders to a surface that was, by design, non-porous and low in moisture. The seemingly simple act of salting a potato chip revealed itself to be a complex problem of physics and surface adhesion, a final battle against randomness that had to be won in the few seconds before the chip was sealed away from the world. The physics of the problem were unforgiving. A simple curtain of salt falling onto the conveyor belt would prove catastrophically inadequate. The chips, moving at several feet per second, presented a chaotic, tumbling target. Salt crystals would simply bounce off the slick, oil-coated surfaces or fall uselessly between the chips onto the conveyor below. The distribution of adhered salt would be governed by pure chance, resulting in a product that was wildly inconsistent, some chips overwhelmingly saline, others receiving no seasoning at all. For an operation built on the doctrine of absolute uniformity, this level of random variation was an unacceptable failure. A new weapon was required, one that could force a controlled, even application of seasoning onto every square millimeter of a moving target. The first decisive countermeasure was mechanical, the seasoning drum. This was not a delicate instrument, but a large rotating stainless steel cylinder, often 10 to 15 feet in length, mounted at a slight downward angle. As the stream of chips fell into the elevated end of the drum, the slow, controlled rotation, typically between 10 and 20 RPM, gently tumbled them over one another. This created a continuous cascade, ensuring that every surface of every chip was momentarily exposed. Inside the drum, a precision dosing system, often a calibrated auger screw, dispensed a continuous metered flow of seasoning. The freshly fried chips, still warm and coated in a thin film of oil, provided just enough surface tack for the fine salt and powder to adhere. The angle of the drum controlled the residence time, ensuring that by the time a chip had tumbled its way to the exit, it had been thoroughly and evenly coated. This was not cooking. It was a continuous mechanical process designed to defeat random distribution through forced interaction. But even the tumbler drum had its limitations. The ultimate solution, a technology that represented the final imposition of order, came from the realm of electrostatics. This system elevated seasoning from a mechanical process to one of particle physics. As the stream of seasoning powder was dispensed from its hopper, it passed through a high-voltage charging grid. This imparted a strong negative electrical charge to each individual salt crystal and flavor particle. The potato chips, meanwhile, moved along a grounded metal conveyor belt. An oil-coated potato chip is an excellent dielectric, or electrical insulator. As the cloud of charged seasoning particles enveloped the neutral chips, a powerful electrostatic attraction was created. Each particle was drawn directly to the surface of the nearest chip, adhering to it with a force far greater than simple tackiness. The effect was not merely adhesion, it was a targeted assault. The electrostatic field created a wraparound effect, pulling particles onto the sides and even the underside of the chips, surfaces that a simple gravity-fed system could never reliably reach. The result was a level of uniformity that was a mathematical impossibility for purely mechanical systems. Furthermore, this method proved devastatingly efficient. The amount of wasted seasoning, or fall-off, was reduced by as much as 50%, a staggering economic victory on an industrial scale. The electrostatic seasoner was the final, definitive weapon in the war for consistency. It guaranteed that the flavor experience of the billionth chip in a production run would be an exact replica of the first. The product in its final form was complete. The streams of perfectly formed, flawlessly seasoned chips, each one a finished testament to victories won over biology and physics, now converged on the final nexus of the production line. Here, the last great operational challenge was not one of creation, but of assembly. The problem was one of overwhelming scale and speed. How to place a precise weight of a fragile, low-density and non-uniform product into its armored vessel at a rate that could keep pace with the factory's multi-ton-per-hour output. A simple volumetric filler was useless. 10 large chips might weigh the same as 20 small ones. The arithmetic of commerce was unforgiving. An average overfill of just a single gram per bag, multiplied by 60 million bags a year on a single line, represented a catastrophic loss of finished product. An underfill was a breach of faith with the consumer. The enemy was imprecision, and the battlefield was a set of scales. The decisive weapon in this final conflict was the multi-head combination weigher. The machine was not a simple scale, but a high-speed microprocessor-controlled statistical engine. The torrent of finished chips was first deposited onto a vibrating central cone, which dispersed them into a series of radial feeder channels. Each channel shuttled a small quantity of chips into one of 14 independent weigh hoppers, or heads. This is where the machine's brutal logic took over. In the span of milliseconds, a central computer measured the precise weight in each of the 14 hoppers. It then performed a near-instantaneous combinatorial analysis, evaluating up to 16,183 possible combinations to find the one group of hoppers whose contents, when added together, came closest to the target fill weight, for instance 40-5 grams, without falling below it. The calculation was instantaneous. The machine's decision was absolute. Once the ideal combination was identified, perhaps hoppers 2, 5, 8 and 13, their gates snapped open in perfect synchronization. The precisely metered charge of chips dropped as a single unit down a forming tube, a polished metal chute around which the composite laminate film from a massive roll was being shaped into a continuous cylinder. As the chips fell, the machine performed its final atmospheric modification. A lance injected its charge of pure nitrogen, purging the oxygen and creating the pressurized pillow pack. The instant the chips settled, placing them inside the not yet sealed bag, a horizontal sealing jaw moved in. This was the final decisive act. A pair of heated metal bars controlled to a temperature of approximately 350 degrees Fahrenheit clamped shut on the laminate film with a precise pressure. This action accomplished two tasks simultaneously. First, it welded the bottom of the next bag in the continuous tube. Second, and most critically, it welded the top of the bag that had just been filled. The heat was just enough, and applied for just long enough, to melt only the innermost sealant layer of polypropylene, fusing it to itself to create a perfect, impenetrable, hermetic seal. In that moment, the war was over. The inert nitrogen atmosphere was locked in. The external world of oxygen, moisture, and light was locked out. A transverse knife sliced the finished bag free, and it fell onto a final conveyor belt, no longer a work in progress, but a finished article of commerce. The entire sequence, from the chip entering the weigher to the sealed bag dropping onto the conveyor, took less than half a second. Operating at a rate of 120 bags per minute, the machine was a blur of seamless motion, a final, chattering testament to industrial certainty. This single machine was the point where all the previous technological threads, the agricultural science of the Kennebec, the thermodynamics of the Fryer, the material science of the composite laminate and the gas chemistry of the nitrogen flush were brought together. The result was not a simple bag of potato chips. It was a self-contained, engineered ecosystem, delivered with a precision and at a speed that Herman Ley, in the trunk of his Model A, could only have understood as a form of industrial magic. The technological victories were now absolute. From the genetic engineering of the Kennebec potato to the statistical perfection of the multi-head weigher, the war against a universe of random variables had been won. The result was a product perfected and a vessel designed for its indefinite preservation. But these weapons had been developed and deployed by two separate parallel industrial empires, each waging its own regional campaign. In the American Southeast, Herman Ley's organization had mastered the potato chip. In the Southwest, another entrepreneur, Charles Elmer Doolin, had waged a nearly identical war with a different raw material. After purchasing a recipe for an extruded corn snack for $100 in 1932, Doolin built the Frito Company into a formidable power, solving the same fundamental problems of consistency, shelf life, and distribution. The year 1961 marked a strategic turning point. The perspective shifted from the factory floor back to the highest level of command and control. In that year, H.W. Ley & Company merged with the Frito Company, creating a single new entity, Frito-Lay Incorporated. On the surface, this was a simple corporate consolidation, a joining of two successful snack food businesses. The deeper truth, however, was that this was not a merger of balance sheets. It was the unification of two of the most effective industrial logistical armies ever created. It was the moment when two powerful, but geographically constrained field armies were combined under a single unified command, creating an operational force of unprecedented national scale. The primary strategic effect was the immediate creation of a truly continental distribution network. Prior to 1961, the two companies were dominant but regional. Ley's 4,000-strong force of driver salesmen controlled the shelves of the Southeast, while Doolin's network held sway in the Southwest and West. The merger instantly resolved this geographic limitation. Fritos and Cheetos could now ride in Lay's trucks into every grocery store in Georgia and the Carolinas. In return, Lay's potato chips moved into Doolin's trucks, conquering the massive growing markets of California and Texas. The result was a single, national direct store delivery system, a private logistical network that could place any product on any shelf, anywhere in the contiguous United States with military precision. This logistical synergy was matched by an equally decisive industrial consolidation. Both companies had arrived at near-identical technological solutions through parallel development. Both had mastered continuous flow frying, high-speed packaging, and the science of composite laminates. The merger allowed for the systematic pooling of decades of research and development. The best practices, patents, and production techniques from both organizations were standardized and deployed across a newly unified production base of over 46 manufacturing plants. The new entity's purchasing power was staggering, allowing it to command favorable terms on everything from millions of tons of potatoes and corn to the millions of pounds of polymeric film required for packaging. This was not mere efficiency. It was the creation of a manufacturing and distribution superpower, an industrial avalanche that smaller regional competitors could not hope to survive. The campaign for national dominance could now begin in earnest. The industrial and logistical superpower created by the 1961 merger now required a field doctrine to translate its overwhelming potential into market dominance. The final, decisive weapon in this campaign was not a new machine or a new material, but a system of human deployment, the Frito-Lay route sales system. On its surface, it appeared to be a simple delivery network. The deeper truth, however, was that this was not a distribution system in the traditional sense. It was a closed-loop command and control network, a private army of over 10,000 salesmen that extended the factory's logic of absolute control all the way to the retail shelf. Where competitors sold their products to third-party wholesalers and distributors, in effect surrendering their product to the chaos of the open market the moment it left the factory, Frito-Lay bypassed this system entirely. From the moment a bag of chips was sealed in its nitrogen-purged vessel, it never left the company's custody until a consumer took it from the shelf. This doctrine of direct store delivery, or DSD, gave Frito-Lay three unassailable strategic advantages. First, it offered absolute control over product freshness. The salesman's primary directive was not to deliver, but to curate. Armed with a strict schedule of pull dates, he would physically inspect the stock on every visit, removing any bag approaching the end of its scientifically determined life cycle. This act of culling stales was a non-negotiable part of the doctrine. It guaranteed that the brand's promise of freshness, engineered at such great expense in the factory, was not squandered in the final few yards of the supply chain. The arithmetic of consumer trust was unforgiving, and Frito-Lay's army ensured it was never put to the test. Second, the system translated into a war for territory fought on the floor of every grocery store in America. The salesman was not a delivery driver. He was a forward-deployed account manager. He did not simply drop a box in the stockroom. He personally wheeled a cart onto the sales floor, cleaned the shelf, meticulously arranged the bags for maximum visual impact, and fought for prime placement at eye level. This direct management of shelf space, a battle measured in inches, ensured that Frito-Lay products were not only present, but dominant, creating a wall of color and branding that relegated competitors to less desirable, lower-velocity locations. Finally, and most critically, each salesman functioned as a forward intelligence agent. Equipped with a handheld order entry device, a technological marvel for its time, he recorded the precise sales data for every product in his store at the moment he restocked the shelf. This information, collected from tens of thousands of stores daily, was transmitted back to regional nerve centers. The result was a river of real-time market intelligence of unprecedented granularity, a live picture of what was selling, where it was selling, and how quickly. This feedback loop allowed production schedules at the 46 manufacturing plants to be adjusted almost instantly based on actual consumer demand, not on historical forecasts. It was the final decisive link closing the circuit between the factory and the customer. This system was Frito-Lay's ultimate triumph, an industrial machine that did not end at the factory gate, but extended its reach to the final moment of purchase. The direct store delivery system was the final expression of the industrial doctrine. This closed-loop network was the material realization of the vision Herman Lay had conceived decades earlier from the trunk of his Model A. Where he once saw crushed bags and rancid product as a logistical puzzle, his successors now presided over a system that guaranteed freshness and market dominance through a doctrine of total control. The factory's discipline did not end at the loading dock. It was projected into every one of the tens of thousands of stores it serviced. The salesman, with his handheld computer and his mandate to cull stales, was the final instrument of process control. The forward agent ensuring the company's promise of perfection was upheld at the final point of conflict, the retail shelf. With this final link in place, all the disparate campaigns, in the laboratory, the field, the factory, and on the road, were unified into a single, self-correcting industrial organism. The story of the potato chip was no longer about a food item. It was about a system engineered to its logical and commercial conclusion. We return then to the suburban kitchen in 1958, to the sharp hiss of escaping nitrogen, to the impossible uniformity of the golden disc and the satisfying crystalline fracture of the first bite. That moment of mundane perfection was not culinary. It was industrial. It was the consumer experiencing the end product of a decades-long war fought on a continental scale. A war waged not with armies, but with engineers, chemists, and statisticians whose battlefield was the very nature of matter and time. The enemy was randomness, and it had been defeated on every front. It was a war against biology, one with a genetically superior potato. A war against physics, one with machines of unrelenting precision. A war against chemistry, one with composite materials and inert atmospheres. A war against geography, won by a logistical network of overwhelming force. A war against chance, won by statistical analysis and real-time data. The perfect golden chip was not a snack. It was a trophy. It was the finished edible artifact of industrial certainty.